Alright, time for another draftphysics.com, debatephysics.com also. But, yeah, as stated, hard to find debate that's in a, reasonable, on the subject kind of debate. So anyway, there is this channel and website called mathandscience.com. And a fellow seems he's had a pretty good career, working at NASA and all kinds of, physics. And on his website, he does have 1/2 mv squared under the word physics, kind of indicating that, he's saying that's really the subject. Now, his videos don't have a whole lot of conversation about the origins of 1/2 mv squared, its history, or why it is what it is, and all of that. And so I will play some of his video clips from different videos where he does talk some about it. And just, I'm going to make these arguments about, basic science. He's a teacher, and I'm sort of arguing that, if you're going to teach, you should be teaching the truth. And that's sort of my critique. And these questions, there's questions to be asked about why science says, and they're legitimate questions, in my opinion, that haven't been answered and that scientists are evading, frankly. I've offered real money to people to answer my questions, and they won't do it. So I'll see if you will. So this video, I'll try to make it brief in the beginning, and then the rest of it you don't have to watch for the details, but I'll just make the primary argument, which is one thing we can know for sure is 1/2 mv squared is not the right answer. There is no energy duality. Momentum is the definition of energy in the universe, and 1/2 mv squared is a complication that makes no sense. It doesn't add any value. It never gives you a better answer, and it's easy to prove that there's just no place for it because it's essentially just what it was called 300 years ago. It's a free energy formula. It breaks physics. It doesn't make physics, and it certainly doesn't deserve to be in this position, in terms of having a formula, stating that this is the truth, because it just isn't. Right, so stating the argument, the counter-argument, as simply as possible. If I can find any circumstance, like Einstein would say, all I need is one experiment and, I can defeat a theory. So if there's any circumstance where, it gets a wrong answer, that's significant. All right, so the competition is between 1/2 mv squared and our momentum. Just simply mass times velocity. That tells you how much motion capacity you have to move something in the universe. The mass indicating how many buckets you have. The velocity indicating how much is in each bucket. Can be understood that simply. Mass is a bank account, and velocity is how much is in each one of the bank accounts. Something like that. It's easy. It's just so simple compared to this. All right, and the simple example is we could just use 10-ton trains versus 5-ton trains. Any inverse relationship, between the mass and velocity. So we're going to give the 5-ton the 10 velocity, all right, and give the 10-ton the 5 velocity. The kinetic energy formula says this object has twice, 2x the energy, the number of joules. So if joules mean anything, it's significant, and this has obviously 1/2 the energy. So simply put, I can just put this stuff on a lever. Okay, so I'm running out of space already. I can make a lever, and I can just put the 10-ton train here, the 10-ton object, the twice as heavy object there, the one object there. They'll oscillate perfectly, meaning the energy goes into gravity, is stored in gravity, comes back out of gravity. Gravity really is potential energy is a whole nother subject, so I'll get to that later. There's no such thing really. It's all active energy, and it's just you tapping it, but whatever. Lots of details that I think are just stated wrong. Anyway, the simple argument is this clearly this clearly moves an amount of distance, and this clearly will always move twice the distance in the same amount of time. Therefore, if it oscillates perfectly, they have to be the same energy. Okay, the fact is I can plow the 10-ton train going 5 miles an hour, which has half the energy, into this side of the lever, and I can produce the 5-ton train going 10 miles an hour. So I can make free energy. So obviously I could use this mechanism, create a system that is a perpetual motion and perpetual energy making machine, because I'm making free energy. I'm not adding any energy, I'm not adding anything to the system, and I'm getting free extra joules out of the system. Twice as many, could be 4 times as many. I just put a half weight object over here, half this weight, 1/4 this weight, and I can have a 4-to-1 ratio. I can make tons and tons of energy really easy. The other simple argument, I gotta erase. Alright, so the other simple argument is a system, any system that stores energy through pressure of either a gas or a liquid. I guess the liquid would be more, gives you a more obvious result. And all I have to do is create cylinders and pistons. And the simple truth is that if I, connect these 2 cylinders together and I do the 10-ton train again, I do the object with twice the mass and half the velocity, and I push it in here, I'm going to displace a certain amount, okay, with the cylinders. And the fact is if this is movable, okay, and I have the little 5 here, I have the half mass here, I will produce twice the displacement here in the same amount of time, and I will move this object with the appropriate extra velocity, and I will create free energy. So 100 joules goes in, 200 joules comes out. And again, I could do the same thing where all I have to do is change the size of that displacer, okay, with a commensurate mass change, and I can make 400. I can, increase the amount of momentum. I can increase the amount of stated joules of energy, and without putting any extra energy into the system. It's free energy. It can't be true. It can't. The 1/2 mv squared is not the right answer. And somebody should be able to explain these 2 experiments and explain how I've made a mistake in what I'm stating, and that this actually doesn't happen when I think and I know it has to happen. There's no alternative, okay? You can't destroy the momentum, and the fact is, that it will produce this result. You will make free energy if you obey the 1/2 mv squared. It's not the right answer. It's bad physics, it's bad logic, it's bad science, and somebody should be willing to fix it. People who want the truth anyway, or care about the truth, should pay attention. Now, I could argue, so I will argue. So now, I won't throw in the other arguments till I get to the other subject I want to get to, that I want an answer to. But come on, there's a history to this, and the history is terrible. And if anybody does any research and recognizes that somebody just made this up, this wasn't some kind of, we have a problem and we need to solve it. No, there was no problem. Newton just explained the whole universe, essentially, and everything was working just fine when this showed up. Okay, it didn't solve something that was broken. It wasn't an answer to, hey, there's a problem in our physics, it doesn't work right. That's not what this is. All right. Alright, so the other subject I'd like you to address is the Eddington experiment, okay, the whole lensing, objects from Earth, and you change its position because the light is bent. Now, the theory is that it's bent 2x as much. I think you probably know that, which seems kind of bizarre, right? It's bizarre first that a force is bent by another force, because that doesn't happen in any other circumstance. You can't hit light into light, you can't hit magnetism into light, you can't hit anything into anything that's moving the speed of light. But it just happens that photons, for whatever reason, okay, one of the things moving the speed of force, is somehow bent. And it's bent twice as much as an electron or a proton or an atom or an elephant. Somehow it is motivated by gravity twice as much as every other thing, even though it's supposed to be almost immaterial, which all seems quite weird. All right, and this is what made Einstein famous. Let's understand this experiment gave Einstein the New York Times headline, made him an international character because he predicted something very bizarre, and it gave him huge credibility in making his, in my opinion, silly relativity theory. Yes, things are relative. I'm not saying they're not relative. I'm saying they're still an absolute universe. So, yeah. The absolute universe comes first. The three dimensions are real. Anyway, so the experiment's crap. Okay, both exploratory teams. So two teams are sent out to go out in an eclipse and do this experiment. You probably know all that. Okay, they both have crappy circumstances. One of them screws up their telescope and has blurry images. The other one has crappy weather. And it's not even a great eclipse anyway. It's 2 o'clock, 2 p.m. Eclipse, well, 2 plus, which means it's, a little low on the horizon, which means it's going through even more atmosphere. And so that's the key argument here, since you worked at NASA, which does things from space. The 400, times better seeing from space, 400 times. So the whole thing that makes this experiment difficult is the fact that it's hard to get a good image of the little star, because the sun wipes it all out because of the atmosphere. So, it's really dodgy kind of business. You can't have an eclipse during the night, so you have to do it during the day, and the sun diffuses through the atmosphere and makes a mess. And, in terms of wiping everything out, but in space, the sun doesn't do that anymore, So there's no atmosphere, so the sun is, bright, 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 and then right next to it is dark, dark, dark. So first off, you don't have the problem of the diffusion of the light, and second, you have so many advantages, and you have 400 times better seeing. All right, so you don't need an eclipse, to do it from space, and you have 400 times better viewing. So you can do it any time of day, any time of the year, any time of the, month, anything. And you have 400 times better seeing. So doing it from the space shuttle or doing it from a space station with a meager telescope, a 30-inch telescope, you'd still have like a 365 times advantage. You could use a tiny telescope and still have a gigantic, huge visibility advantage. So you have an experiment that's dodgy. It's never really been repeated with superior technology from the ground. It's one of the most famous experiments there could be in terms of making Einstein, and you haven't done it. So you did go to the trouble to stand on the moon and drop a hammer and drop a feather, to prove Newton right, but you haven't redone, what is a critical experiment, frankly. I mean, it's saying something amazing, and yet NASA hasn't done it. So first, I don't want to say there's a conspiracy because I don't believe in conspiracies, but it seems to me that why is there so little enthusiasm among NASA's scientists to do this experiment with this 400 times advantage? Now, yes, you'll say, well, we have other instrumentality that tells us. Well, all of that instrumentality doesn't pay any attention to the fact that the sun has this huge atmosphere, of charged particles all the way around it, and that frankly, the atmosphere doesn't have like a line to it, where you go from a high density of atoms to a low density of atoms. Now, it's a very blurry line, because there are lots of different velocities that the particles have, so there's still lots of junk out here. And so, yes, doing radar experiments through the corona of suns or objects isn't the same, because you can expect to get a lot of scatter, and you can expect, frankly, every path. The photons will take every path. They'll take the longest path, and they'll take the shortest path. So if you want any signal at all, you get some signal. But anyway, I don't want to have to debunk all of those things. I could just argue the lensing images. You like math. Well, you know that every single one of those lensing images has horrible math. I mean, the the yeah, you know, the Einstein ring is hardly a ring. It's supposed to be a perfect ring, and it's supposed to be so damn thin you can't even see it. So Einstein would argue you can't even see an Einstein ring. He said it because, frankly, it's only going to be about 6 pixels in width because gravity isn't a great lens. So I really don't want to argue all the other ways scientists, physicists might say they have proved this 2x bending. I just want to understand why the simple experiment, the one that really could prove it, with the 400 times better resolution from space, hasn't been done from space. I mean, this seems like something NASA could do in about 15 minutes, and I just don't understand why it hasn't been done, and why you don't think it should be done, why it isn't an important experiment to do, all of that. It doesn't make any sense to me. And yes, I would argue that this is ludicrous. The fact that light is bent by gravity, in my opinion, is nonsense. And the fact that it's happening twice as much is double nonsense. But you can't really, there's no theory for making a force affect a force, frankly. It just doesn't happen. Alright. Electron force does not bang into electron force. Yeah. Charge doesn't bang into charge. It bangs into other charges. Has to reflect off of them. Has to go all the way to them, affect them, and, you know, anyway. Alright, so now I'll just do the backup to all of this, which is lots of the little ideas that physicists have that I think are just wrong. Alright, so I guess I'll first do just a little preliminary stuff before I start playing his video, and then I can respond to each individual little element. But okay, so you have this MV thing, and you can think of it as, okay, the velocity is the speed, and the mass is a capacity to make yourself known. Okay, you have to, something has to carry the speed. Okay, you could say it simply. Alright, I would argue that we could probably reduce the whole thing to just electrons and protons and say they're the elemental bit, and let's just make it an electron for the sake of the argument. So what does a typical electron do in the universe? Now, I would argue that the force, okay, and the matter are two different things. Okay, they're the two distinct things in the universe. So there's two things. There's matter bits and there's force bits, and that the whole universe is just made of this stuff moving the speed of light. So the force equals the speed of light. Okay, it's the speed of force, and that includes magnetism, gravity. All this stuff is all the same stuff, and you're just changing its configuration. You're just changing, you know, light is just this stuff at a frequency. You know, I can make the different arguments about what magnetism is, but that requires a little more pieces to this argument, and I want to create those more pieces yet. Alright, so understanding that if you're in a universe full of BBs all moving the speed of light, and I put something in there that reflects the BBs, you can understand that that makes the BBs more energetic, and, I mean, increases the pressure of the universe. And the BBs will constantly bombard it, and if we understand that there's some mechanism, some interaction that takes place when a force bit hits a matter bit. Now, the simple thing is people say, okay, I throw something, I hit it, the thing I threw stops, and the thing I hit moves. It doesn't work like that. This is eternal energy, okay? It never stops. It's always rowing, okay? So you can think of it as rower, I don't care. And you can think of the ocean, and it's rowing without a boat, which means it doesn't, you know, can't do anything, but just speeds around rowing without a boat. And when it gets in a boat, it obviously has to now push the boat. So the idea would be is that the force bits, the little tiny stuff, is going to interact with everything, you know, in the universe, and it's going to, everything's just going to jiggle in the little tiny bit of differential there is at any one moment from different angles getting hit. So it's sort of a Lesage argument. It's not Lesage, but it's sort of like one. Okay, which isn't a bad thing, because frankly that's what they use to, that's mock gravity, frankly, and they use that to teach relativity. But anyway, alright, so the simple argument is the electron, let's just say it's an electron, gets hit by one of these little force bits. It would stick, okay, because that's just the rule. And this, now the mass of this and this has mass, okay? This isn't a massless thing, this quanta of energy. It has some infinitesimally small Planck-style mass. And now it's just a typical kinematic type interaction in the sense that you just sit there and figure out the mass of both objects, and now the new velocity won't be the speed of light. The new velocity will be the mass combined mass divided into the previous velocity, so it'll be something less than the speed of light. Okay, so let's just say it was weighed the same, then we'd say it was half. Okay, so if the force and the mass weighed the same, but you know, I think it's obvious that the masses are bigger than the force, but whatever. The idea would be then that if something came from the opposite direction, now this mass is moving half the speed of light because it has something pushing it, and say a force comes from the opposite direction and hits it, it's going to do the Newton's cradle thing in the sense that now you have two opposing forces and they will essentially now reflect. Okay, both forces will reflect, and now this mass won't be moving at all. So another one comes in, both of them reflect, the universe is restored, so to speak. The energy this had taken out of the universe is now back in the universe, and you end up with a mass, and you have two force bits going like this. All right. So there's no way to collect energy beyond just a differential. And so you could have two of these here. You could have three of them. You could have four of them, any number. And that would give you a force velocity in a direction, and it can never reach the speed of force, right? The pushers are going the speed of light. They can never, okay, have the added burden of carrying the mass and still move the speed of light. So it creates the speed limit without any Einstein complications, because you can never go faster than the stuff that's actually pushing you. And they can be at any angle. So every angle is, you could have a force in this direction on an electron. The electron can be carrying a differential in this direction. It could be carrying differentials in these different directions, and it does the math. And it can never collect force on both directions. So it can never have stuff going this way. It can never have a deficit in its checking account and an asset in its checking account. Okay, so these are the bank accounts. Every direction would be a bank account. And in every account, there's either a plus, you have motion, or you don't have motion. You either have equilibrium, 0, or you have stuff on one side. There's never stuff on both sides of the register. So it doesn't collect over time any artifactual energy. It's all real. So it's really pushing. All right, the great thing about this is it explains why there's gravity, because it explains quite simply why the energy goes into the earth going the speed of light. It is degraded, okay, by the atoms in the earth moving, and when those atoms are moving, getting pushed, the electrons and protons are getting pushed, they're collecting the energy, slowing it down, and so now less comes out than went in, because every single atom that's moving, every single electron that's moving is being actively pushed, and that active pushing requires consumption of the speed of light energy from the universe. So essentially matter's a heat sink. It absorbs energy because it produces heat. Remember, heat is evidence of its absorption of energy from the universe. All right. And that explains why there's gravity. So that's a big bonus of understanding this as motion. So motion isn't you send a little force bit, the force bit stops, and the matter bit goes. That's not how to understand it. It does stick, but it still obeys the rule that if a counter force hits it, it loses its force this way and this way. So it's not too complex. So anyway, that's the background. It's a push universe. There's no such thing as a pull. So if something's moving, it's because it does have this imbalance. And if it has an imbalance, frankly, if there's an electron going this way somewhere in the universe, there's probably an electron going this way somewhere in the universe, because you always have to account for the conservation of the total energy in the total universe, blah, 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 blah. All right. So that as a foundation. We will play some of the video. It takes a while to get to the exact kinetic energy argument. So I'd like to make these other arguments that friction is not a force. Friction is just you giving away the energy you have, the extra imbalance you have. If something's moving, it has an imbalance. It has more force bits going this way than going this way. And the simple argument is you're going to start giving away your extra until you become neutral again. counter force. There's no force, essentially. It's a sink. Again, it's not applying a force to you, it's applying a sink. It's applying a place for your energy to go. Your imbalance is now the imbalance in the other objects that are now moving. You've given them your imbalance. Alright. Yeah. Okay, so we'll play the video. Alright, so at this point he's talking about how the superposition of the forces, and that essentially you could say something like, the math, the mass does the math. So different forces act on it. The mass will figure out whatever that net product is and move in that direction. I would argue that but the math it's doing is, on a millisecond scale, and the truth is it's not really going to follow that perfect line. It's going to actually be an least line. It's going to actually have the fact that it's moving in more than one direction built into it, to some extent. But anyway, it doesn't really matter. The real point is that this isn't true. There's two kinds of matter, right? There's the elemental bits, the electrons and protons. Then there's the atomic bits, okay, where electrons and protons are in combination. So I would argue that as a simple way of understanding why the distinction between how matter moves, big matter, and how little matter moves is like the resonating, oscillating thing that moves. So I can put a spring between two objects and then put them on an air track and they can do this thing. The spring can be oscillating. And the fact is that the object will move like an inchworm. So it won't move the same as just linear motion. It'll stop and then move and then stop and then move. One object's always moving, one object's always stationary. And I can make that even more complicated. So you could argue that if I put an electron and a proton and an electron together, I could create a complex oscillator where there's attraction and repulsion, and frankly it oscillates with a resonant function of some kind. That I would argue that that's what's fooled physics. That's what the 400 extra particles they've created, the tau and the muons and all of that stuff, are really just combinations of electrons and protons in resonators, little machines that are oscillating. And that's why they have very different energy levels. But anyway, continuing. We'll play the video.
Then, of course, it's equal to mass times acceleration. We get a single acceleration out of it.
So again, it's mass times velocity, and the acceleration is just how you get to the new velocity. So I did argue in the previous video, but I'll state it again, that Newton didn't say F equals ma. He said F equals the change in your momentum over any unit of time. So you can pick your seconds, or you can pick hours, or you can pick days, or you could pick the total. And if you pick the total amount of time of an experiment, then it reduces simply to force equals the change in your momentum. And obviously in all these experiments we're not changing the mass, so it really just is saying force equals the change in your velocity, in the context of your mass. But that's what it's saying. Force is weight, force is pressure, force is energy, and force is momentum. And there is no 1/2 mv squared.
The way you might see that written in a book is really that the sum of these forces is equal to the mass times acceleration. This is a better version of Newton's laws, because what you do is you...
All right, so it would be better if it was force equals mv, because that's what Newton basically said. So acceleration you convert into the formula you use to detect acceleration, which is measuring distance and time, and you just keep doing that over and over again. So as I did state in the other video, this is going to come down to also this idea of gravity as a force applied per second. Okay, that's how you calculate it. You use a unit, a second, and then you know that it's a continuous force, so it's per second. And your notation for that is to use the squared symbol. It's not a correct way to use the symbols. It's using the wrong word. It's bad vocabulary. It breaks logic because you're using the word heavy for something that's not heavy. You're cheating the word because it isn't really a squared function. So per second is not forever. It's not for a certain number of seconds. It's not a squared function. It's not an explicit number. It's who knows how many seconds you did it. So until you know how many seconds, then you know what to multiply it by. By multiplying by itself, you're getting the same answer for completely different circumstances. 10 seconds, you multiply it times 10 seconds. You don't multiply it times the speed. It's going 30 miles an hour. Why would I multiply 30 times 30 when I only did it for 10 seconds? It's just wrong notation, and it breaks your physics.
Add up all the forces, and the resultant force, but you're adding them vectorially, the resultant force is what matters to produce the acceleration. Another way you might see it is you might see it as F net is equal to ma, right? The net force. So what I'm trying to say is when you have multiple forces acting, you resolve it to a single force, and that single force behaves equal to mass times, and you can produce.
Right, so I would argue that that's not what, so the subatomic particles are still stuck with all those little energies, and yes, there's a net product to where it'll end up at point B. It'll end up going a direction, but it's not really going there, as smoothly, where the bigger compound matter is really adding up what's happening inside the nucleus, the pressure between the electrons and protons, all of that stuff is getting added up. And the fact is that the net atom will move in the direction. Even though its pieces are doing a lot of jiggling still, it will end up moving in the net direction. But it'll have a lot of waste in it. Just like a school of fish can end up going in a direction, and there's still fish swimming in the wrong direction some of the time. So some period of the time that the school is moving, there's fish that are actually swimming in the wrong direction. Well, the same is true for an atom or a big clump of mass. I can move 5 miles an hour in a direction. Doesn't mean that every bit inside of me is moving in that direction. I'm sitting in gravity now. My argument to you would be that gravity is pushing me into the earth. Okay, so there's definitely stuff inside of me moving into the earth at this second. And there's clearly the earth is pushing back, and there's other stuff moving out. And the number of things moving down and the number of things moving up are equal, and that's why I don't go anywhere. But the fact is there's stuff inside of me moving up, and there's stuff inside of me moving down.
That acceleration there. All right. Now, what does it actually mean graphically? I'll do a couple of different things. I'm going to draw some pictures. But what I'll use is my magnet here. Let's say I'm producing a force. This is kind of more like this going here. I'm pushing here. And as the thing starts moving, my force is still being applied. You can imagine it being like a rocket thruster attached to the object. So
let's just understand that when you add a rocket thruster attached to the object, now they're just one object. And all you're doing is taking your fuel tank and saying, I'm going to let something out of it. So if I attach a lunar module or whatever I attach to a rocket engine, it's all just part of the rocket engine now. That's all it is. And the engine is the thing that's going to create the thrust. So you're going to push gas out of a nozzle. That creates a certain amount of thrust on its own. Then you're going to ignite it in a small space, which is going to make it expand. And now you're creating even more pressure, and you just sit there and use your little cone on the end of your nozzle to sit there and shoot all of that energy to reflect it all in the direction that forces you to go the opposite direction, because you're essentially being pushed. Because you're giving away a ton of energy going in a direction. You gave away this way out of the tank. It's not hitting the wall of the tank anymore. This way is left, and now you're stuck with a bunch of this way. And that's why you move. And the constant pressure argument is again of time. It's all about time. So that's just another part of your physics completely broken. I mean, you have the work equation where you're talking about how far something travels, when no, it's about how long are you in the force. So in gravity, I can put something 4 times higher than something else. I drop something from a height, and then I drop something from 4 times higher. What happens? It only reaches twice the velocity, 2. And more importantly, it goes that 4 times the distance in only twice the time. So that means it's only in the force of gravity. It's only free falling in gravity for twice the time, which means it's only collecting energy while it's falling. It can't collect energy once it hits the ground. Once it hits the ground, the energy goes right through it into the ground. Just like the whatever rocket ship you have ends up, as soon as you attach it to your tank of fuel, it just becomes part of the tank. Same argument in a sense. Well, anyway, continuing.
As I move it, I'm still pushing it, then it goes.
Right, and so it's just about how long you're pushing something. And this example is horrible in the sense that we know, friction is eating it up as soon as you give it to it. So as soon as you give it any energy, the energy is getting absorbed by the friction because the magnet is sticking to the surface and creating lots of abrasion. And so all of the energy is consumed almost instantaneously. So you're almost just creating a little curved line into gravity, into a complete standstill. You're pushing this way, all the energy is just going into friction, so you never really store any in the object.
Faster and faster and faster. I'll go over here. Because the force is still in contact with the object, well, if I can hold it, it goes faster and faster and faster.
Right, but it can only go faster and faster and faster if your hand goes faster and faster and faster. If your hand stops going faster and faster and faster, then it just goes 30 miles an hour and it can't go any faster and it can't take any energy from you. So once the pusher and me are going the same speed, the pusher's not doing any work. Okay, I'm not going to gain any velocity. Okay, we're just two objects moving 30 miles an hour and there's no longer any forced contact. There's no electricity traveling between us. There's nothing changing between us. So the pusher has to have a higher speed. Now that's the catch, right? Gravity gives us a constant amount. And the reason why it's a constant amount is because gravity is really going the speed of light. So it's just how many little bits going the speed of light are hitting you that decides how fast you're going to go. So the more you collect, the faster you go, because you're collecting speed of light for a period of time, and that's what you're collecting. So your speed, the pusher always has to have the capacity. If you're going to go faster, the pressure has to increase. So the only way you can make that thing go faster is you have to increase your velocity, which means you're increasing the pressure you're pushing the object with.
Because as the thing is moving, the force is still being applied. As long as the force is being applied, the acceleration is still happening.
Right, but it can't still happen if the object pushing is pushing at a constant rate. So again, if it's pushing at 30 miles an hour, it isn't going to work. Now, if you're saying it's pushing at 10 pounds per square inch, and then you just keep increasing your speed to keep 10 pounds between you and the scale. So if I put a scale between you and that magnet, and we can watch the scale, then we can watch that, you're applying a constant 10 pounds of pressure. Yes, your speed is going to increase, and your speed will increase just to keep that 10. So you're just going to say, I'm going to go as fast as I have to go to keep it 10 pounds of pressure. So 10 pounds of pressure, you get there, and yes, it becomes, as soon as this starts moving, you have to apply more velocity at your end to keep the 10 pounds of pressure. So, this analogy needs more details.
Right? So if I continue applying the force throughout the entire time, it's accelerating the whole time. But let's say that I accelerate a little ways, and then I just let go of the force, and then the thing is going to go coasting in a constant state of motion.
Right. Well, obviously that won't because of friction, and that, in my opinion, is an unsolved question. So I would argue to you that electrons and protons don't do that. That they do in fact drag to a halt. Okay, so you can't push them and make them go forever because they will in fact hit gravity. They'll hit the elemental force in the universe, and it will consume their energy. And the only things that can keep moving are the oscillators, the objects, the nuclear objects like helium nucleuses that have enough parts in them to create an internal mechanism that can overcome the drag. I'd argue that that's the actual truth. Whether anybody will ever get to it, we'll see.
So if you have a rocket thruster, firing, I'm accelerating the whole time, but then when the rocket cuts off, I'm coasting at a constant velocity. And everything starts floating in deep space because I'm at a constant velocity. And in a
Right, but that's only for complex matter, not the elemental matter.
inertial frame of motion. So graphically, I can draw this, and I can say here's an object with mass m, and I'm going to apply a constant force to it, and then I'm going to have some.
So he's going to apply a constant pressure. So that's the catch. Right. It's not a constant force, it's a constant pressure. A constant amount of weight. Weight is energy. Pressure is energy. That's energy.
Velocity. So I'm going to put a force right here. Now, at some snapshot in time later, I'm applying exactly the same force. Well, what's going to happen? The velocity is going to be bigger than it was.
Right. So we know if that force number was you're going 30 miles an hour, and that's your force. Well, we know the mass will reach 30 miles an hour, and then you will not be applying any more force. So it won't be a constant force anymore. So clearly the force is actually has to be something that has the capacity to increase its energy proportional to the energy increase in the mass.
Because force is equal to mass times acceleration. That means that there is an acceleration happening, so the velocity must be getting bigger. So the acceleration is an arrow represented right here. The arrow for the acceleration is the same length, but acceleration is making the velocity bigger the whole time. That's what it's basically doing.
Right. So this is really just a gravity argument that they always put, sideways. So they always talk about forces as if gravity was the only force in the universe, which, is just sort of silly, frankly. Because it is a force being applied that is, in fact, going the speed of light, and that you're applying the force based on how many units of the speed of light you give the object. And so I could use a rain analogy that if you run from point A to point B, there's rain, and you run through the rain, you're less wet than if you stand in the rain, frankly. So it's just about how much time you're in this differential of the force being applied. But the force has to be applied, and it has to have the capacity to run faster. So clearly the force has the capacity to give more. So you're really just saying that when it's raining, it doesn't matter where I'm standing, I'm going to get just as wet. So it's just about time. So in this equation, he's saying time is forever. You're always in the rain, and you're always going to collect the same amount of force. So that's what kind of force he's created. He's created a force that's really rain. Okay, it's a bunch of pushers. It's not one thing pushing, because one thing pushing would have a velocity. So this isn't about an object applying a force. This is about an elemental force. This is about force bits going the speed of light and being capable of giving you a number of their pushers, a number of rowers for your boat. And they're adding a rower consistently per unit of time. You have 10 seats. Well, let's say you had an infinite number of seats in your boat. They're just adding rowers. Okay, per second, adding a rower, adding a rower, adding a rower. Your boat's going faster and faster because it's adding a rower. And you're gaining more and more velocity because you already have a velocity, and the new rower is just adding to that velocity.
And then if I go here and do the same thing, I'm still applying my force to the same mass, but now because I'm still applying that force, that velocity is even bigger. Again, in the same way.
So this is just Galileo, okay? 1, 3, 5, 7. This is just the fact that as you go faster and you add more force, you go faster, and you're still going faster and faster because you're starting from a faster position. So when you're going 20 miles an hour, I add pressure, I add a rower. The whole time you were going 20, now you're going to go 30. And then you're going to go 40, and then you're going to go 50. I guess the catch is, though, that, gravity is 9.8 meters per second, but in the first second, you only go 4.5 meters, right? So, 4.8 meters, 9 meters. So it gets a little bit complicated.
And then I have an acceleration there. So acceleration is a vector. I need to put my vector arrowheads on these. You see, the acceleration vector is the same, because an acceleration is meters per second squared. That's meters per
Okay, it's not meters per second squared. So this is the big, I'm sorry, frankly, I don't know what to call it, because it's just lying, it's wrong, and it's Per second squared does not mean you square the seconds. You can't put the squared symbol on it. The squared symbol means you're just multiplying the quantity times the quantity. You're not doing that. You're saying that it's per second for a number of seconds. It could be 10 seconds, it could be 20 seconds, it could be 50 seconds, it could be forever. The fact is that's an important difference in what you're multiplying. You want to multiply it times the actual number of seconds, not the seconds, not the velocity.
Second per second. That means every second that goes by, I'm adding a certain number of meters per second to the object.
Right. That is not squaring. Okay. So it's just wrong to say you're squaring it. It's not. The square number is not going to be the same as 15 seconds, 20 seconds, 50 seconds. They can't all have the same answer.
And so every second that goes by, the velocity arrow gets bigger by the same amount. All right? Now let's do the same exact thing, but I'll turn it around and I'll change the direction of the forces. Let's say I start right here. Initially, my velocity is going this way. Right? There's my mass.
He's going to get to kinetic energy eventually, but he's not going to say much, frankly. So I have there's another 4-minute video he did. I probably should play that because this video is going to get long, but it's all right. Yeah, maybe I'll make a second part and put it on the website. But anyway.
And what I'm going to do now is I'm going to be firing a thruster in this direction. So now you see, whereas these were lined up, here my force is actually going contrary to the velocity. It's not
right, and so it's not going to like these two are going to be competing. The fact is that contrary force is going to take the energy from the other one. So it's going to lose the energy because you're going to be hitting it in the opposite direction, reflecting all the extra energy it collected. So if you look at it on the electron's perspective, you're just saying, okay, the electron is traveling because it has these extra rowers. Well, you're basically going to have a collision of a kind that's going to oblige those rowers to fall out of the boat.
not trying to make it bigger, it's trying to make it smaller. Right, so what's going to happen in the next...
We'll jump ahead a little because this isn't getting to the real good point.
Same force right here, right? But what's going to happen is it's going to slow down, and then it's going to start accelerating. Well, it's accelerating the same, but it's basically going to slow down, and then it's going to start to go this way. And
right. So if I'm plowing into light hitting me, the light will take whatever I'm plowing into it with, and it's going to slowly. I'm going to lose my energy. Then I'll have no energy, and then it's going to start giving me its energy. I'll start collecting. So at first I start losing, and then I start collecting.
So I guess I'll change it to probably red. Then I'm going to have a small velocity. The arrow is the same. Because what's happening, force, velocity and acceleration are different. So I'm subtracting velocity, and now I'm still subtracting, so I'm still making it bigger in this direction. Acceleration is acting in this way. The force is right here. The acceleration is acting in the same exact direction.
So he's emphasizing the idea that the force is always in the direction of the acceleration. And one would argue that, of course, it has to be. It's energy in a direction. So you have to account for that. And the only way you're going to account for it is you're going to either lose your forward motion or you're going to start going backwards. But to say it explicitly works when his diagram overtly is showing the arrows going in opposite directions is a little bit wrong. You're not really accelerating in the opposite direction. You're decelerating in the forward direction, right? So if I'm slowing down because something's pushing against me, you don't really call that an acceleration in the opposite direction. You're in fact decelerating. I'm taking the energy out. Friction takes the energy out. All right? It's decelerating you. It's taking away the motion you have in a direction. It's not pushing you, okay, backwards. So it doesn't work. So I probably shouldn't emphasize this as being a key thing to understanding that the force and the acceleration are always in the same direction, because they technically really aren't.
In all cases. So the velocity and the acceleration don't have to line up, but eventually the thing will slow down, and if it's accelerating the whole time, it'll scoot back the other direction.
Right, but you started the video by saying they always line up, and it's really important you understand this. They always line up, they're always going in the same direction, so you're just sort of contradicting yourself. He did this in another point where he was making a point about forces don't push matter, and then he says in another video exactly the opposite, that yes, if matter is moving, it was pushed by a force.
These pictures are just intended to give you an idea of how force and acceleration and velocity all behave with respect to one another. And now we want to go back and talk about a little bit more about the definition of what a Newton is. I told you in the beginning that a Newton is basically the force you feel in your hand from a medium-sized apple. It's pretty close to a quarter.
It's right. So it's just a weight. So that's all we got. It's a weight. It's a pressure. I put 100 grams on my hand and applying a pressure because of gravity. Gravity's hitting it, and then it's going right through it, and it's going into my hand, and the pressure that it's collecting is now pushing on my hand. It's a weight. It's pressure. And that's all that, and then a joule is just dropping that thing, letting it collect gravitational energy, letting it collect acceleration, all right, gaining more little bits of force, pushing it. It's gaining little bits, moving the speed of light. It's collecting rain. It's now heavy with the rain it collected, and then it hits. That's a joule. A joule is also a weight. When it hits, what's it going to do to the ground? It's going to apply pressure. It's going to apply a weight. It's not going to weigh 100 grams anymore. It's not going to weigh its atomic weight anymore. It's going to weigh its atomic weight moving a velocity. Mass times velocity. It's going to have momentum. The feather and the hammer drop at the same rate, but clearly the hammer has collected a ton of momentum.
Quarter of a pound. It's not exactly a quarter pound, but it's pretty close to that. Feel an apple on Earth's gravity. That's what it feels like. Let's go and talk a little more detail about this. Now that we know that F is equal to ma, right? Now that we know this, then what we know.
Right. So this is it just makes a mess out of something really simple. The force is the pressure, is the weight, is the momentum. It's the mv. Your mass has to have a velocity to weigh anything. Gravity gives it a velocity. That's why you weigh something on the scale. It's because if I put you on the scale, you move the scale until the pressure going up is equal to the pressure going down. So you clearly weigh something because gravity gave you velocity. That's why you weigh something. If I push you this way, you weigh something because of what I'm pushing. Does it matter whether I smash a baby into the turn on my computer button? I could put a baby between the button that turns on my computer. I could push on a baby, and then the baby pushes on the button. Or I could push on an elephant, and it pushes on the button. It's all the same thing. It doesn't make any difference. The only thing that matters is the pushing force. Doesn't matter what I'm pushing, but it will matter in the sense that both of them will acquire the same amount of momentum. So the baby will clearly move faster than the elephant will into the button. But once I have them up to the same velocity, it won't matter.
Is that if we know that 1 is equal to 1 times 1, right? So if we have 1 Newton right here, that's going to be the same thing as 1 kilogram accelerating at 1 meters per second squared.
Right. So that's 1/10 of the gravitational pressure. And so you could sort of understand that if I want to double your mass, I just go 10 of those, and I've doubled your mass. But anyway.
You see 1 is equal to 1 times 1, and these are the correct units in there. So what this is saying is that 1 Newton...
So what it's saying is if I had a 1 kilogram and I pushed it sideways instead of down, as gravity does, I have to go 1 meter per second, okay, to create the pressure of a Newton. And if I want to do a joule, I have to push it at that rate of 1 meter per second, okay, for 10 seconds, right? No. Doesn't matter. I don't know if it matters how many seconds I do it for. I'm pushing it at a speed, so the seconds will be decided by how fast it's going for the 1 meter, so I don't have to worry about that part. But clearly it's not, see, he just wrote it here, 1 meter per second squared. It's 1 meter per second. There's no necessary, this square shouldn't be here. Okay, so just understand, this is where they go all wrong. Okay, it's 1 kilogram moving 1 meter per second. That's its velocity. That velocity, you could assume it to be forever. You can assume it to be 10 minutes. You can assume it to be anything. It doesn't matter. You don't need this square. It's moving at a rate of 1 meter per second.
Is the force that is required to take 1 kilogram...
I mean, when a runner's running around a track, they don't say he's running, 4 miles an hour. They don't say hours squared. He's running 4 miles an hour squared. No, they don't do that. He's running at a rate. The car goes 50 miles an hour. It's not 50 miles an hour squared.
Kilogram of mass and accelerate it by 1 meter per second squared. So this is something you could figure out in a lab. You could take 1 kilogram of mass, you can push it with a certain amount of force and measure the resulting motion, and when it accelerates exactly 1 meter per second squared, that is the force that you're pushing on it. It has to be exactly 1 Newton, and that works out to be the amount of force you feel in your hand.
So that's 100 grams. So what you have to do is find the one where 100 grams equals 100 grams. I don't know, you know. What speed do I have to go sideways to create, okay, my weight? So for my atomic weight to equal my scale weight, how fast do I have to hit the scale? That should be calculable. You know, I should be able to calculate that. But it's going to be something like, yes, it's going to be like 1 meter per second or something like that.
From, you know, an apple. All right, let's jump into
I think I did calculate. It was something like 2 miles an hour or something. I can't remember.
our first problem and get some practice actually calculating this. The first problem says...
It might be 20, actually, because it's going to duplicate what gravity's doing. So we've just decided how much we weigh based on gravity, you know, and so gravity's the... And it does current, you know, gravity, the good thing about gravity is that it's pretty close to that 10 meters per second number. You know, it's 9 something, but I'm just saying it's close, which makes the math easier. All right, so I don't know why we're on word problems. So somehow I have loaded the wrong video. Crap. That's disappointing. All right, so I really thought this is the one where he talks about kinetic energy, but it's not here. Damn. All right, well, I'll go find it. Well, I found the right video, but yes, we're already hitting an hour, so I'll make another video. You know, maybe only if necessary, frankly. You know, we'll see if I can provoke him in answering the questions I asked in this video. And then we can get into the subject of potential energy and the jargon they use to hide the fact that the kinetic energy formula is just a silly duality formula. You already have a perfectly good definition of energy in the word momentum, and this kinetic energy competing theory. You know, really, you can't have two contradictory theories of energy. It's just silly, frankly. I mean, I shouldn't have to explain that to smart people. But anyway, apparently I do have to. So we'll see where it goes, and then I'll... You know, there's already a video, an hour's worth of video of me playing his other video and dealing with some of the Newtonian mechanics, and but I really want to get to his description of kinetic energy because, frankly, you'll see that he doesn't really explain it at all. Why 1/2 mv squared is all necessary. How it answers questions better than momentum. He doesn't make those head-to-head comparisons. So anyway. So, till the next time and such and so forth and whatnot. This has been draftphysics.com, debatephysics.com also, and such.